Greetings, this is Purple Target, and welcome to my tutorial Let's Play KSP series, Krash Test Kerbals, Episode 1 TAC 7, Ejection and SOIs. Currently using Kerbal Space program version 0.90. At Crash and Learn, we explore just enough rocket science to be dangerous, and learn how to abuse math instead of the other way around, to get our Kerbal out into the depths of space more or less where we want them for fun and profit, as opposed to accidentally stranding them in random orbits around their sun. For today's objectives, we're going to follow up the last couple episodes about Hohmann transfers and look at what happens when we want to leave the gravitational influence of the planet or moon that we're at, and how to plan out burns accordingly so that we can plan a burn from inside the sphere of influence of one planet to allow an efficient transfer to another SOI. We'll look at what is the sphere of influence and how it affects spacecraft that are leaving, particularly how the direction at which you exit an SOI translates to the orbit that you end up with once outside. Anything that is going to leave an SOI needs to know what escape velocity is required to achieve such freedom. We'll look at what happens when a spacecraft intercepts an SOI and how that will affect its final orbit around the destination. This is useful for making fine course corrections to avoid unnecessary tears and heartache when you arrive around Duna going the wrong direction to RV with your cleverly prepositioned space station. And we'll get out the last bit of math for Hohmann transfers, or indeed any transfer that would leave an SOI. Determining where to place the maneuver node on the orbit of the current planet, which will get you aligned properly with the outside motion of the planet itself, so that once you leave the SOI, you'll waste a minimum of fuel fixing wonky orbits.
Continue count. 3, 2, 1.
To get started, we're going to send up some probes to mark out the extents of the SOIs around Kerbal and its moons, and at long last we'll be launching Jeb into space for a quick flyby of the moon to show you the finer points of SOI intercepts. KSP uses a two-body problem for determining force of gravity in the game. That is, it only really considers the spacecraft and the one planet, moon, or star around which the spacecraft is currently orbiting. The real universe considers the effects of all the bodies, and thus the n-body problems. And those kind of calculations would even make my computer melt at the thought of it. It would allow for cool things like Lagrange points and odd orbital perturbations that would cause all our satellites to fall out of sync and need constant station keeping, but if I wanted a maintenance simulator, I'd probably get the same satisfaction by washing my dishes more often. Anyways, with the two-body problem, the sphere of influence defines the volume of space around a planet or moon where objects within are affected by the gravity of that body. The fun part about things like gravity is that it tends to be invisible, and funny enough, so are the spheres of influence around the planets in KSP. But anytime a spacecraft crosses the boundary from one SOI to another, funny things start to happen to the orbits, as the gravity of the new body takes over or lets go. This transition isn't always intuitive, and the fact that it's invisible probably doesn't help. But if there's anything that should be apparent by now, it's that at Krash Test Kerbals we love to put up beacons all over the place just for fun and visualization. Thus these triple beacon packages have been dispatched to mark out the outer extents of the SOIs for Kerbal, Mun, and Minimus. This will end up at about 90% of the SOIs, so we should know pretty close to the approximate extent. As we've said, the spacecraft will be ruled by the gravity of the planet while inside its SOI. And we know from previous episodes how to calculate our orbital velocity for any given altitude in order to get a circular orbit. And we know that if we add to that velocity, we start getting more and more elliptical orbits, which we can use for Hohmann transfers. But there's a limit. Once the apoapse of a transfer orbit touches the SOI, the orbit breaks and the trajectory changes to a hyperbolic shape, where the spacecraft still has some kinetic energy left over once it's crossed the SOI threshold. That is, there's still some outbound velocity left over once the gravity from that planet is no longer strong enough to act on it. At that point, the spacecraft has escaped the SOI and has escaped the gravitational pull of the planet it left behind. I'm sure you'll be shocked to learn that this is what's known as escape velocity. And at any altitude, it's governed by this equation, which you may notice is strikingly similar to the orbital velocity equation. It doesn't get much simpler than that. What you'll find is that it'll always be about a 41% addition to whatever the orbital velocity is for that same altitude, because all that's added is the square root of 2, which is like 1.414-ish. Compared to the 2279 meters per second to make our parking orbit around Kerbin, we don't need even another 1000 delta V to make the 3223 required to escape from the grasp of the planet entirely. This is one of the reasons why they say once you're in orbit, you're halfway to anywhere. It's also why there's a large number of players out there with several Kerbals needing rescue from solar orbits, since building a rocket to hit that velocity even going straight up is quite possible to manage even by accident. Come on, tell me you haven't done it at least once.
Checklist complete. Continue count. 3, 2, 1.
Now this will be a first for Krash Test Kerbals. For launch 14, we're actually sending a currently live Kerbal into space, and none other than Jeb himself. I know, shocking. And if anyone is wondering what happened to launch 13, well, not that I'm superstitious or anything, but numbering things with 13 is kind of like going to war. Don't take anything into battle that you want to keep. Such it is with painting the number 13 on anything. Anyway, we've loaded Jeb into a pretty standard Corolla-type Mun lander, which is a small, just under 5-ton spacecraft with about 2,600 meters per second delta V, which is about enough to complete a Mun landing and return, as long as it gets a decent push into a translunar injection. For today, though, Jeb will only be going into and out of orbit to show the SOI transitions and ejection angles, so that'll be plenty. We've loaded it onto a Topaz Light Kerbal Space vehicle rated for 5 tons, and yes, I'm making up these categories because real-life programs don't need to split hairs this badly, but we're also not 1/11th scale. I'm sure everyone remembers from a previous episode how we calculated the delta V for the first and second burns to reach the Mun, as well as the 60-degree phase angle for the initial translunar injection burn. Now, for pretty much any transfer orbit, we need to keep in mind how speeds work. Heading up to the Mun, we have a smaller orbital period, but when we reach the AP, the spacecraft is moving slowest, and the Mun in a circular orbit is going roughly the same velocity all the time, so it can't help but smack into the spacecraft just as it's hanging there. This means that when you're transferring to higher orbits, your spacecraft is pretty much guaranteed to enter somewhere along the front of the SOI. If you're exactly still and on the orbital path when the SOI hits you and the spacecraft doesn't try to move sideways a little, then the planet will hit the spacecraft shortly thereafter, causing the spacecraft to suffer a rapid unplanned disassembly similar to that of a bug hitting a windshield. Lethal braking, however, is not good for Jeb's health. If the AP is shallow and catches the inside of the SOI, then you're likely to end up getting a prograde orbit around the destination. Or if the AP is long and gets the outside of the SOI, then you'll probably end up with a retrograde orbit. I say probably because it not only depends on the entry point that the spacecraft enters the SOI, but also the vector of the spacecraft at that time. When the spacecraft crosses the SOI, the vector of the spacecraft is modified by the motion of the planet as it changes reference frames. Don't bother taking notes on this one, no hard numbers, just a few arrows to show roughly how the change works. As the Mun and the spacecraft are both orbiting Kerbin, they both have their own velocity vectors. The Mun is going 542 meters per second, and in this case the spacecraft intercepts the Mun SOI well before it's reached its AP. It still has a velocity represented by the green arrow. Now once inside the SOI, everything is relative to the Mun now. So the 542 meters per second of the MUN's velocity needs to be applied in the opposite direction against the spacecraft. Then the spacecraft itself still had its green vector from before, and once both these vectors are applied, we'd get the new red vector, which is the brand spanking new spacecraft vector relative to the MUN, at the instant that it is inside the MUN's SOI. And the MUN's gravity takes effect to bend the trajectory around in the prograde direction. Similarly, arriving at the SOI above or below the equator of the destination is going to set you up on some kind of inclined or even polar orbit, depending on how you arrive. This can be handy if done intentionally. For example, survey satellites that would want to scan the whole planet should be in near polar orbits to trace the entire ground. However, RVs with equatorial stations, or if you want maximum flexibility to leave the planet again whenever the stars align, so to speak, then you'll probably be wanting to align the inclination as best you can before entering the SOI to avoid costly inclination changes afterwards. Hopefully this will help to visualize or understand what the various orbital lines are trying to tell you when you're planning maneuvers. During rescue missions for Kerbals stranded in orbit around the MUN, it's handy to arrive in the orbit that's headed in the same direction as the rescuees, since changing direction is liable to result in two sets of Kerbals in need of rescue. Because that never happens either. Now the other thing to chat about is ejection angles. There's a couple of ways to deal with SOI transfers. You can put a spacecraft just above escape velocity and let it poke its head out just outside the SOI, and then you can maneuver directly from there. The problem there is that you spend more time than needed just moseying out of the SOI, which may mess up your phase angles, it increases your gravity losses, and you lose any O-berth bonuses by going fast near the planet. Can be done, but we'll use a little bit of math to avoid all that. We already looked at the way vectors change coming into the SOI, and so the opposite goes when we leave the SOI. When we're planning, say, an interplanetary journey, we would want to maneuver as if the spacecraft was in the planet's orbit, or the planet. But our maneuver nodes are actually stuck on the orbit inside the SOI, so the nodes don't translate the same. Let's take a moment to review our maneuver nodes. We'll have the radials, otherwise known as the straight up and the you're not going to space today directions, which will torque the orbit, adjusting both the AP and PE at the same time, and is occasionally handy for specific cases and in small doses, but it's not generally efficient. So if we leave the MUN SOI headed towards or away from the parent body, being Kerbin, then we would end up with a radial type effect on the transfer orbit once we exit the MUN's SOI. Similarly, if we leave headed up or down relative to the orbital plane, then we would end up with the normal or anti-normal effects, and the transfer orbit will end up with some amount of inclination. Whenever we're doing Hohmann transfers, we're looking at a prograde or retrograde burn to efficiently raise or lower our AP or PE for the transfer, right? We want to exit the SOI as close to parallel as we can with the planet's own prograde or retrograde direction. That way, whatever velocity we exit with, it's directly aligned with the motion of the planet, and we don't waste any energy off to the radials or the normal directions. The ejection angle will tell us the angle between the prograde or retrograde direction that we want to exit in, and backtrack it along the direction of our spacecraft's orbit to see where we want to place our maneuver node. This is a multi-step process, but we'll get an idea of what it is that we're trying to calculate. First, we need the delta V we need left over by the time we leave the SOI. Remember, gravity is slowing everything down as the spacecraft is on its way to the SOI boundary. But once we leave, we still want the delta V left over in order to make the actual maneuver a reality. Whatever our Hamming calculations tell us, that's the Vx or excess velocity that we need. We'll run the numbers to this equation, and in this case we're using the planet of the SOI that we're leaving for things like the gravitational parameter and the radius of the spacecraft in its parking orbit and the radius of the planet's SOI. That will give us the VEJ or ejection velocity, which is the velocity that the spacecraft needs to achieve during its departure burn to have the required VXS once the spacecraft reaches the edge of the SOI. If we need a small VXS, then we don't need as large an ejection velocity, and the ejection angle will be close to the opposite side of the prograde that we're aiming for. If on the other hand we need lots of delta V on leaving the SOI, then we need a larger ejection velocity. And that will also mean less time in the SOI as the spacecraft departs, so less bending from gravity drag, so it can be closer to 90 degrees from the departure that we want. The main takeaway here is that our ejection burn is generally going to be somewhere in this quarter between 90 to 180 degrees from where we want to leave. And of course it doesn't matter if we want to leave retrograde, just measure from the planet's retrograde direction and backtrack along the parking orbit. In these diagrams the parking orbit is prograde, but you could just mirror them for a retrograde orbit. Now, Jeb has been hanging around the MUN for a while and probably wants to go home now, so we'll run through this example. We saw in episode 1 TAC 4 about Hammond's, we need 365 meters per second in order to circularize at the MUN's radius. And Hammond transfers being reversible, this also means that that's the delta V we need to lower the PE from the MUN down to our parking orbit. It's a retrograde maneuver. We want to slow down in order to drop the PE, so we need to depart the MUN in its retrograde direction. Jeb is also in a retrograde orbit, so we'll measure the angle from the MUN's retrograde counterclockwise. We can run the 365 into our equation, the radius of the MUN, as well as the 10-kilometer parking orbit and the MUN's gravitational parameter, and the SOI radius, and it gives us 836.6 meters per second, which is a little less than 300 more than what the spacecraft is doing already. Now the real fun begins. One equation would be extra messy, so we'll run down this list of equations. I highly recommend spreadsheets for this to avoid rounding errors or the insanity of trying to copy these numbers from one calculator to another. First is our specific orbital energy, and it's a very useful equation in general, so keep it around for some other episode. The H is mostly to feed the eccentricity equation to allow simplicity, and from the eccentricity, the arc cosine will provide an angle off the 180 degree position. So the ejection angle being from the other side of the planet, we just need to take the difference from 180 degrees. So when all's said and done, we'll want to place the ejection burn at about 143 degrees back from the retrograde direction. When it's all said and done, of course, you can fiddle with the maneuver node location and make sure everything is lining up right. It's not like I'm going to measure 143 degrees exactly with a protractor on screen, but I can tell by eyeball roughly where the node should be placed as a start. Main things to look for: your burn is about the right delta V, and the trajectory at the SOI exit is parallel to the planet's orbit line, and the next orbit isn't twisted up or down from the exit point. It should be a smooth line to trace from the exit to the AP of the new orbit. If the orbit is twisting up or down, then there's probably some radial action going on, and moving the node location should clear it up. This is a good time to bring up space oddities, rules to live and crash by. Don't obsess about the orbit direction. Orbits are symmetrical and reversible, so no matter if your spacecraft is going prograde or retrograde, it'll probably still be able to manage the mission you've set for it. The only exceptions will be if you need to be going a certain direction to, say, RV with a space station or another satellite, in which case it pays to be going in the same direction as your target. Now, if you've opted for a highly inclined or polar orbit going in, then you might have some choices to make. Without doing an expensive inclination change first, the orbital plane just may not line up at all for a prograde or retrograde exit that you may want at the time that you want it. Basically, you have two choices. You can burn just past escape velocity to make the poke out of the SOI and maneuver once you're clear. Yes, as I said, somewhat inefficient in the grand scheme, but you'll likely waste far less delta V in the inherent inefficiencies than you would doing an inclination change. Or, if time isn't a factor, you can wait until the planetary prograde aligns better with your orbital plane, close enough that you can do a regular exit using the same angle. For something like returning from the Mun, this is no problem since you're just dropping into the planet's gravity well. For something like a return trip from Duna, however, the phase angles needed might pose a problem with waiting for orbits to align. Don't chase efficiencies. Do what makes sense. Burning at PE just because someone says it's more efficient won't matter if the PE isn't at your optimum injection angle location. And for a roughly circular orbit, it's not like that little difference in altitude will offer much in the way of savings anyway. Drive the mission. We talked about how the SOI intercepts happen at the AP, where the spacecraft would intercept the SOI along the leading edge as the planet or moon would be traveling faster. For transfers down to lower orbits where the spacecraft is approaching its PE near the target, this is reversed, and the spacecraft will likely be going faster than the target planet and slam into the SOI somewhere along the back half. By now, you should be able to calculate the ejection angles for yourself, although they are nice to have, as maneuver nodes make them pretty easy to modify as needed. Then again, in early career mode where you don't necessarily get maneuver nodes, calculating may be useful. I hope you'll at least be able to better visualize where the ejection node is most likely to be placed, 90 to 180 degrees back from your desired exit direction, and how to figure out what direction is desired. We've also covered how the spacecraft will enter and leave an SOI, and what that means to your planned transfer maneuvers, and hopefully how to read the patch conics a little better to understand how the spacecraft will behave once it's inside the SOI. Jeb apparently has way too much fuel left, since he didn't get to land on the Mun. Maybe next time. This has been Purple Target at Crash and Learn. Peace out.